take a zoom at the proton. Then we see it's composed by particles such as the up quark. You can find also the down quark. And you can also find something called gluon. So gluon is a particle that connects two quarks, so quark, quark, gluon, so like a little spring that prevents them from getting apart. Currently, we cannot compute the properties of the quarks and gluons in the proton from first principles. So what we need to do, we need to extract this information about the proton structure from experimental data. At the LHC, we take two protons, the two protons that get close to each other, and then we will get one gluon from this proton and another gluon from the other proton. These two gluons interact and produce, for example, a pair of top quark. If we can measure these top quarks, we gain information about the gluons in the proton. However, there is a big caveat here that I'm assuming that the interactions between the top quarks and the gluons follow the standard model. But we know that there is physics beyond the standard model. So perhaps the top quarks interact in a slightly different way. And we don't have here a gluon, but we have some other particle, which is not in the standard model. What we are doing is trying to see how we can disentangle these two effects. So we are trying to separate, say, what is the proton structure from possible new physics effects. This can be done by analyzing experimental data, but allowing the interaction to be different from the standard model. When we go to very high energies, the effects are logarithmic, so it's a very smooth. However, if this is what is happening, in the case of new physics, the effects are of the form, they vary with the energy in a much more abrupt way than the QCD effects. The key figure in our paper is in page 4. So in blue, you see the standard model. So this is that if there is no extra physics, and you see that the behavior is flat. However, if you have new physics effects, in this case, in the SM effective field theory, you see that the trend is very different. So the beautiful thing of this result is that you don't need to do a specific search for extra particles. Just by measuring your normal, say, processes, you can constrain or even identify possible deviations that might hint to new physics beyond the standard model.